So now let's prove this theorem. This, I guess, proposition. So part A. So we'll start with so we'll say we'll use the contrapositive. So say that H intersect K is not equal to 1. So there exists an X which is not equal to 1, and that X is in H intersect K. And then so we picked some X here. I'll erase the not equal to 1 part. And so by the way, if I'm using 1 here, and I guess I used E over here, that's totally interchangeable. Maybe I should put E right here just to be consistent. But anyways, so now I have this X which is in both of these subgroups, and okay, let's pick, say, well, we know both of them are subgroups, so let's say, let's use the fact that H is a subgroup, so X inverse is in H, as H is a subgroup. So now I can say f of X inverse X. And so this guy is in K because it's in both. This guy is in H because H is a subgroup, and I mean, it also has to be in both because but we didn't even need to say that it was in both. So what's going to happen, we didn't need to say that it was in both to just put it into this map, because this component requires things that are in H, right? And this component requires things that are in K. So we use the fact that this is in K and this is in H. And, well, this is just a multiplication map. That's 1. That's something that's in the kernel. So X inverse X is in the kernel. And so that map is not injective. And okay, so that's one direction. Now the other direction, so conversely, so now we suppose that H intersect with K equals the identity. I guess I should say the set containing the identity there. And H inverse K equals the identity, and we want to show that the map is injective. So let's pick 2 elements. Pick H1 K1 and H2 K2 such that their images are the same, right? F of H1 K1 equals F of H2 K2. Well, but that's just the same thing as saying, you know, H1 K1 equals H2 K2, because this is just, the map F is just multiplication. Okay. Now, what we can do is let's collect all of the terms on each side here, meaning I'll multiply on the left. Let's see, I'll multiply on the left by H1 inverse, and on the right by K2 inverse. So I'll have K1 K2 inverse equals H1 inverse H2. Now, well, so now what we can see is this is in K, That's by the fact that, K is a subgroup. And this part, that's in H. So this element must be in both of them. Therefore, that's equal to 1. Or, yeah, I guess I should say E. Again, just to be consistent. This is the identity, though. And, so because it's the identity, well, we have, we can just say now, right? K1, K2 inverse equals the identity. That means that K1 equals K2. And similarly, H1 equals H2. So because K1 equals K2 and H1 equals H2, that shows that F is injective. Because we picked two things which map to the same thing and proved that they have to be the same thing. Okay, that was part A. Now let's do part B. So how's part B going to work? So remember what we were trying to prove. We were trying to prove F is a morphism if and only if the elements of H commute with the elements of K. So let's take a look at, so we want to think about a morphism. So we want to think about f of AB and f of A, f of B, right? And if f is a morphism, we'll have something like this. So, okay, so I've written this equation. Now let's write something in for A and B. So let's say A is H1, K1, and B is H2, K2, and okay, now what I can do here is, sort of make some room and this will be H1, K1. This will be H2, K2. And then when you multiply these together, you'll get H1, K1, or will you? No, you'll get H1, H2, H1, H2, K1, K2. And, a lot of times when we're talking about maps on product groups, we don't write the extra set of parentheses for the tuple. And then this over here is going to be f of H1, K1, and then f of B will be f of H2, K2. Okay, so we want to compare these. So now we can write out what this is. This is just multiplication, so this will be H1, H2, K1, K2. And this will be H1, K1, H2, K2. So when are these equal? Well, they're equal if H2, K1 is equal to K1, H2. Yeah, K1, H2. And, well, here's the thing. H2 was an arbitrary element of H, and so was K1. K1 was an arbitrary element of H. So this will be, if and only if all of these things commute, then this will work, and that will be a homomorphism. So that will prove part B for us.